All right, okay. So let me start from the top. Welcome everyone to the second series of the Automated Market Maker. I hope you guys are having a great time over where you are. So let me just jump right into it. Today we're going to introduce the different models of the AMM, Automated Market Maker, and then we'll just rehash what we learned in lesson 1. So I'm trying to share my screen at the moment. Great. So AMM models. I hope you guys can see my screen. Hello? Hello?
Hey, we can see the screen. Go ahead.
All right, great. Sorry about that. Anyway, so so lesson 1 was basically about understanding what AMM is, what the protocol is, pretty much how it works, why the need AMM exists in the DeFi space, and pretty much we understood things about liquidity pools, what it meant, and which is actually a crowdsourced collection of crypto assets, and that liquidity pools are usually provided by liquidity providers, right? These are people who in turn deposit their assets into the pools. So basically that's just a wrap of lesson 1. So today we're talking about the different AMM models. Now, currently as the market exists, we have what they call constant function market makers, right? These are usually the first generation of AMM, which was made popular by protocols such as Uniswap and Banco. These exchanges are based on a constant function, whereby the combined assets of the reserves are based on the trading pairs, which must remain unchanged. So in this category, you have of constant function market makers, you have models like the constant product market maker, the constant sum market maker, and constant mean market makers. And then we'll get into what this means, why are they different, and how do they operate. So let's start from the first. Constant product market maker, right? This was the first type of CFMMs to emerge and popularized by the decentralized exchange Banco, right? So if you remember from the lesson 1, whereby I spoke about a particular mathematical model that was being used by market makers, which is X multiplied by Y equals to K, right? A constant product market maker uses that particular mathematical model, right, to establish a range of prices of 2 tokens according to the available quantities, liquidity of each token. By the way, you can ask me any question at any point in time if you feel free to jump in. So the supply of each of token X increases, right? While the supply of Y must decrease, right? And vice versa. So to maintain this constant K, right? These 2 conditions must exist. If token Y increases, token X. If token X increases, token Y must go down. If token Y must increase, token X must go down, right? And then you have a graph which I'll show is that you get a hyperbola, right? In terms of the situation it is. So this happens because at increasingly higher prices, right, we approach infinity at both ends of either the token X or the token Y. So this is usually the graph for a constant product market maker, right? This is just basically what it looks like, right? So basically this is what it is, and there's nothing more to it. So let's just keep moving on. So the constant sum market maker, right? Basically this type of model, right, is ideal for zero price impact trade, but does not provide infinity liquidity, right? So what do I mean by zero price impact trade? For every trade of, let's say, USDT, add to the BNB chain, right? BNB token chain, there is something calculated called slippage. Slippage is in terms of the volatility, right? Value that is being provided in the current market. So those are the slippage are taken as price impacts, right, on top of the transaction, right? And so a constant sum market maker will not take into recognition the price impact of that trade, right? It will just give you what you requested for. And so they usually follow the formula X plus Y equals to K, right? We create a straight line when plotted, right? So this model allows for people who want to drain more reserve of the main chain reference price between tokens that are not equal to 1 plus 1. So this is like a more technical explanation of what a constant sum market maker is, right? So this sort of situation will destroy one side of the liquidity pool. Remember, I said there's an X token or Y token, and both of them must equal to the to K, right, at all times. But this particular constant sum market maker will destroy, let's say, token X and leave Y, right, which doesn't make sense in terms of the liquidity pool, right? So that situation will leave the liquidity residing not just one of the assets, and therefore no more liquidity for the traders, right? So because of this situation, the constant sum market maker model is really used, right? So this is a graphic depicting the function of a constant sum market maker. You see it's quite different. While this one is more tailed shape, right? This is just a straight line. So it's really not giving us value as much as we want, right? Then the constant mean market maker, right? So this type enables the creation of AMM that have more than 2 tokens and weighted outside of the standard 50 to 50 distribution model. Again, if you take the word 50 to 50 distribution model, you go back to the same equation, X multiplied by Y equals A, right? So in this model, you have the formula is pretty much different, right? You have 3 assets, and the equation must be X multiplied by Y multiplied by Z to the power of 0.5, which is 1/2, equals to K, right? So what does this mean in general? You have variable exposure to different assets in the pool, right? And you can enable swap between any of the pool assets. So you have 3 tokens. You have USDT, you have Price, you have any of the other ones, and you can swap, right, between the quantities of each particular token, right, to the next one. And that's what the constant mean market maker does, right? So these are some of the models that we have, right? Constant mean market maker, constant sum market maker, constant product market maker, right? And because these are all first generation automated market maker models, we have issues with them. Because of course all first generation things do have challenges. They are not full functionality yet. They are in market one. So one of the challenges of the first generation model is impairment loss, and this can refer to the difference in value over time between depositing a token in an AM versus simply holding the token in a wallet. What do I mean by difference in value over time? Depositing token in versus holding tokens in the wallet, right? So in lesson 1, I gave an example of a fixed deposit, right? Account, a bank account, fixed deposit. So you drop some money, you drop some of your cash into a fixed deposit. The bank gives you a rate or an interest rate whereby in 6 months you come back and take this amount. In 12 months you come back and take this amount, right? Now, if that fixed deposit was being run by a smart contract, right? There will be a difference in value by time if you compare 6 months to 12 months. Versus there's an interest that will be accrued to you versus if you held your tokens in your wallet without trading them, right? So that is the difference, right? That's an impermanent loss, what we mean, right? So this loss occurs in markets whereby there are market-wide price of tokens inside the AMM and diverges in any direction, whether towards the X value or towards the Y value, right? So there is a term I use called arbitrators, right? And these are people who maintain the price of assets within that portfolio in accordance to the market price in exchange for profit. So those are people who normally give their tokens out, right, to such AMM, to the AMM to try and get profit. So because this AMM don't automatically adjust the exchange rate, they require this sort of people to help maintain the price of the assets, right? So sometimes an arbitrator on the buys an underpriced asset or sell overpriced asset until the prices offered by the AMM match market-wide prices, right, of external markets. So the profit extracted by these people is siphoned from the pockets of liquidity providers, e.g. creating a loss, right? So another challenge of first generation AMMs are low capital efficiency, right? And this means that the traditional AMM designs require large amounts of liquidity to achieve same level of price impact, just like an order book-based exchange, right? So this is due to the fact of a substantial portion of AMM liquidity is available only when the pricing curve begins to turn exponential. This results to a situation where most liquidity will never be used by rational traders due to the extreme price impact experience. So in this situation, right, low capital efficiency AMMs are always referred to sometimes as lazy liquidity, right? Because they have no control over the prices which are being offered to traders, and their liquidity is often underutilized and poorly provisioned, right? Meanwhile, market makers on other book exchanges can control exactly the price points at which they want to buy and sell tokens, right? This leads to a very high capital efficiency, right? And trade-off of requiring active participation and oversight of liquidity provisioning. So I know as at the end of first class, by the way, any question? Any questions so far? All right. So I know as at the end of the first class, I did give out an assignment saying we should compare and contrast the different types of AMMs out there. I gave a list: SushiSwap, Uniswap, and the others as much as we could find. I don't know if anyone was able to do that assignment. You could just put your answers in the chat. Let me see. Okay, so this was supposed to be an interactive session, but I will give a couple of the examples that I have done, right? And I will still expect participants in this session to still do a bit more research, dive into some of the